Hello, my name is Jake Rhodes. My major is instrumentation technology, and I'm part of the group that's giving a presentation on Pascal's law as is proposed by Blaise Pascal. Pascal's law states that any change in pressure applied to a confined incompressible fluid is transmitted undiminished in all directions throughout the fluid and to the walls of its container. In simpler terms, if you apply pressure to a fluid in a closed system, the pressure spreads equally everywhere inside. This principle is the foundation for hydraulic systems. Some everyday applications of Pascal's law include car brakes, dental chairs, hydraulic lifts, and syringes. In the field of fluid mechanics, which is a branch of classical mechanics, one important focus area is hydrostatics, the study of fluids at rest and the pressure within a fluid. Pascal's law falls under this area. It states that any change in pressure applied to a confined, incompressible fluid is transmitted undiminished in all directions throughout the fluid and to the walls of its container. This principle is widely applied in mechanical engineering, medical devices, heavy equipment, and many other common applications. Blaise Pascal, who lived from 1623 to 1662, was a French physicist, mathematician, and inventor, and made key contributions to the study of atmospheric pressure, formulated Pascal's law, and even created one of the earliest mechanical calculators known as the Pascaline. An interesting fact about Pascal is that he challenged Aristotle's idea of horror vacui, or nature's fear of vacuum, by demonstrating that vacuums can exist. Today, the unit of pressure is called the Pascal, and it is abbreviated as PA. It's named in his honor. Pascal demonstrated his principle through experiments with mercury columns and barometers. He showed that pressure in a fluid is distributed equally in all directions. He also performed experiments using vertical columns of liquid to observe how pressure changes with depth. Pascal faced many challenges while demonstrating his principle. His experimental hardware was fragile, glass tubes for barometers that were hand-blown, easily cracked, and difficult to seal watertight. The fluids he used were also problematic. Mercury, though dense and effective, was expensive, hard to handle, and extremely toxic. Spills often ruined experiments and posed serious health risks. He didn't have accurate pressure gauges, so he had to rely on measuring the height of liquid columns. Even small temperature changes could throw off his readings. Then there were the logistics: how test how pressure changed with altitude. Pascal's team had to transport delicate glassware and mercury up a mountain of 1,400 meters elevation using mules and assistants. Many glass tubes were broken that day. Finally, Pascal had to overcome conceptual resistance. Many scholars at the time denied the existence of vacuums, arguing that hidden vapors filled the tubes. Because of this skepticism, Pascal had to repeat his demonstration multiple times to convince others. Pascal set out to understand atmospheric pressure and challenged the belief that vacuums could not exist. He wanted to build on Torricelli's earlier work with barometers and aimed to prove that pressure could be transmitted through fluids. Pascal's work validated the experience of atmospheric pressure and vacuums. It paved the way for the creation of the early hydraulic devices and sparked further studies in fluid mechanics and pressure-based systems. His discoveries also inspired later inventions, including syringes and the hydraulic press.
Hello, my name is Nelson Gomez, and I'm part of the Parsons Law Group. And so, pretty much, I'm a big modern experimental process. So, today we study Parsons Law with much more advanced setups. Modern experiments uses pistons, synthetic hydraulic fluids, pressure sensors, and sealed systems to measure force transmission precisely. Oil-based fluids are common because of their stability and lubrication properties. So moving on to the next slide, we have different modern approaches. Our tools have evolved significantly. Today's pressure gauges, synthetic materials, and safety valves allow hydraulic systems to be far safer and more efficient than Parsons' early um, apparatus. So moving on to the next slide, the applications are pretty much everywhere, from car brakes and aircraft control systems to dentist chairs and spacecraft hydraulics. Parsons' law underpins technology across countless industries. For the next slide, we have future expectations of research. Looking ahead, Parsons' law is guiding the development of miniaturized hydraulic systems used in soft robotics, microsurgery, prosthetics, and even AI interrogated devices. So, all of this is really important for the future research for scientists, physicists, and that pretty much industry. So, for our next slide, we have relevance of question to topic. Our example problem directly uses Parsons' law. It calculates how an implied pressure on one piston translates to the force application to another. So it says, two post workshop lift raises vehicles roughly 1.5 meters for under car services. Input piston area is 5 centimeters. Lift piston area is 350 centimeters. So the technician pushes 150 newtons, the pressure transmitted under diminished by Parsons' law. So equal pressure multiplies force by A2 divided by A1, which equals 70, letting a modest push lift a 1-ton car. So for the benefits of understanding this question, understanding these calculations is crucial for engineers designing safe, reliable systems, from elevators to mechanical pumps. So the engineers are pretty much using these calculations to help them design safe and efficient systems. So for my final slide, pretty much we've developed our question carefully, choosing realistic variables that reflect real-world applications of hydraulic multiplication. So through this process, we've avoided overly simple and overly theoretical examples to our presentation. So I accidentally forgot a slide. So for this slide, we have uniqueness of question. So pretty much our question stands out because it requires understanding the relationship between pressure and area while applying real unit conversations and practical thinking. So here it has the hydraulic lift question uses real lift specs. A1 equals 5 centimeters squared, and then you have A2 equals 350 centimeters squared, and F1 equals 150 newtons. So you have from that hydraulic lift question to your typical textbook questions, which is find out the output force if A2 equals 100 centimeters squared. So that's kind of the differences between our questions and the textbook's questions you might get. So yeah, anyways, enjoy the rest of our slideshow.
All right, so on the right here is our hydraulic lift schematic, and the hand pump piston is right here, which is going to be our A1. The area for that is 5 centimeters squared, and the force pushing on it is going to be F1, which is 150 newtons. And on the right over here is the big ram under the car, which is going to be our A2 with an area of 350 centimeters squared. And because Pascal's law says that pressure is transmitted undiminished, that same pressure acts on both pistons, setting us up to calculate the lifting force, F2. Now, for our relevant formulas and constants. Our formula is going to be P equals F divided by A, which is Pascal's law. And so our symbols here, or variables, are going to be P, and uh, that stands for pressure throughout the fluid. And its units are pascals, PA. And the value it has in our question is that it's calculated within the first step. Uh, F1 is going to be the input force on the hand pump. That's going to be uh, shown in newtons, and you know we discussed that force in the previous slide was 150 newtons. Uh, then we get to A1, which is the input piston area of the hand pump. Uh, that is going to be shown in meters squared, and for A1 is 5 centimeters, which is equal to 5 times 10 raised to the negative fourth power meters. F2 is our output lift force on the car end. This is also going to be displayed in newtons, and this is our unknown variable we are solving for. A2 is going to be the lift piston area that lifts the car up. This is going to be shown in meters squared, and we already shown that this is 350 centimeters, uh, which is equal to 3.5 times 10 raised to the negative second power meters. And then we have G, which is acceleration due to gravity, which is meters per second, and 9.81 meters per second. Now, on to solving the example question. First step is to convert the areas to meters squared. So we have our A1 is equal to 5 centimeters squared, which is 5 times 10 raised to the negative fourth power. And A2 is 350 centimeters squared, which is 3.5 times 10 raised to the negative second power. Next, we're going to find the common pressure, which we will be using Pascal's law. P equals F1 divided by A1, which equals 150 newtons, divided by 5 times 10 raised to the negative fourth meters per second squared, which equals 3 times 10 raised to the fifth pascals. Then we calculate the output force on the lift piston. This is F2 equals P times A2, which is equal to 3.0 times 10 raised to the fifth pascals times 3.5 times 10 raised to the negative second power meters per second, meters squared, sorry, which ultimately comes to 1.05 times 10 raised to the fourth power newtons. Then we convert force to vehicle mass, which is meters equals F2 divided by acceleration due to gravity, which is equal to 1.05 times 10 raised to the fourth newtons divided by 9.81 meters per second raised to the negative second power, which is approximately 1.07 times 10 raised to the third kilograms. So the solution to this is that the maximum vehicle mass should be about 1.1 metric tons. Next is our final solution and applicability. So the unit consistency is that F in is in newtons, A is meters squared, P is in pascals, which is Newton meters, and the final mass in kilograms after dividing by G. So the sanity check is that the force ratio is approximately, A2 divided by A1 equals 70, and then 150 newtons times, I didn't put commas here, 7,010,500 newtons matches computed F2. Within the lift specification, bend pack BP10 rated capacity, which is the lift sheet that we used, is approximately 4,535 kilograms or 10,000 pounds. Our load is 1.1 tons, which is less than 4.5 tons, which places it well within the safe operating range. And then it's direct application of Pascal's law. The same pressure on both sides. Delta P is transmitted undiminished. Demonstrates force multiplication principle used in brakes, presses, and medical beds. And next step extension is we could theoretically add a 20% safety factor, which would make the maximum allowable vehicle mass to be around 900 kilograms. Uh, Next, for our additional information, uh, Pascal also developed the Pascaline calculator, which is an early mechanical calculator. Uh, he also laid the groundwork for probability theory and vacuums, and his writings influenced math, philosophy, and physics. Uh, for surprising findings, hydraulics are everywhere. In uh, I work right now in a chemical plant, but I've worked in refineries, I've worked in fabrication shops and everything like that, and I'm around hydraulic equipment all the time. Like I've operated equipment that is hydraulic, like forklifts and other things of the sort. Uh, I never really knew that dentist chairs, you know, use the same type of stuff to do what they do, which boils down to the same P equals F divided by A logic. Uh, Next is the small push, like on the hydraulic the hand pump. The small push can translate into a huge lift. Just, calculating a 70 times force boost just from a 15 kilogram push made Pascal's law feel tangible and way beyond textbook numbers. History meets modern tech. Blaise Pascal's 17th century barrel stunt directly underpins today's soft robotic grippers and microfluidic pumps. Respect for experimental pioneers. Uh, Hauling mercury barometers up a mountain without any pressure gauges, showed kind of just how much persistence early scientists needed to actually get their things done. And then, it goes even further whenever a lot of the scientific minded people kind of just doubted his experiments altogether, and he had to continuously repeat his experiments to, get people on board with what he was trying to prove. And then a takeaway from my career, I kind of already went into this, but I'm working towards a process engineering degree. Uh, I've worked around hydraulic equipment before, without necessarily knowing that that's what it was, but uh, it kind of just gives me, the want to check the units and real world specs first. Numbers aren't abstract. They can, they kind of the manufacturer sets safety limits for a reason, and I'm more the I like I have kids and a family. I kind of would want to err on the side of anything that keeps me coming home at the end of the day. Uh, for the project summary, we explored the origin, evolution, and real world use of Pascal's law. This project showed how timeless scientific principles support modern life. And then here is a slide of references that we used for the information provided and for the images, and then the data sheet for the uh, lift that we used for our question. And that's all. Thank you.